So in this problem, you're looking at a tubule that's in the kidney, and you have flow going through, with details given in the problem statement here on the speed here. So the question here is, what's the force, the reactionary force basically needed to keep this section of the tubule stationary under these conditions? And I want you to make sure that you include the pressure force and the body forces. So let's start as always here with a find statement. So in this case, we're looking for FR, I'll call it, or the force needed to keep this tubule stationary. So let's make a diagram real quick. So if we walk through this, making this diagram, I'm going to pull up a PowerPoint here. So this is that section of the tubule, and that'll be our system, will be this section of the tubule. So let's add some of the important information or labels that we need to add here. First, I'm going to label, this will be the velocity in here, and this will be the velocity out. And then we need to identify unit vectors, normal unit vectors for the in and the out. And these are always vectors that are perpendicular to the surface point of flow, pointing out. So you'll see the in is pointing out, the vector is pointing out on both entrances, or the entrance and the exit. And I labeled those as unit vector in I and in J. Then we also need to put the pressure vectors in. The pressure vectors will always be acting into the system, and I'll call it the pressure in and the pressure out with PI and PJ. And then we need to we'll have a body force, and I'll indicate it working at somewhere I guess is close to the center of mass here. And then we're looking for the reaction force. This is the force we're looking for that keeps this tubule section stationary. And then of course we'll need a coordinate system. So we'll have this be the X direction, and then up will be the positive Y direction. So I'm going to take this image now, that'll be our diagram, and let's put it as my diagram here. So now we can go to the analyze for these kinds of problems. So for the analyze, we first, as always, we'll start with the assumptions we're going to assume. In this case, it's going to be an open system. We've got mass crossing the system boundary, so it's open. It's non-reactive. In the momentum cases, though, it's not really an important assumption. And then we're going to assume that it's steady state, that the momentum of this system, if it's going to remain stationary, needs to not change. So we'll call it steady state. Now let's put a basis. In this case, we said that the flow was going at ABC centimeters per minute. Let's put ABC is equal to, or let's call it to the m dot is going to be ABC centimeters per minute, but we need to then multiply that by the density of the fluid. And so in this case, that means we need to, for our basis, we need to assign ABC. Let's say my ABC was, let's say it's 294, let's say. and we need our density. And here the specific gravity is 1.02, so 1.02 times 1 gram per ml. So there's our density. So our mass flow rate, oh, we also need area of flow, right, to get this, because this is going to cancel here, so we need our area, because this is going to be times area. And the area in this case is going to be equal to pi times the density squared divided by 4. And so we need a diameter was 20 micrometers. And so I have to define a micrometer. Okay, so here's our mass flow rate. So from the given information, that is the basis. So now we need any other given information. Let's put in some given information and extra if we need it. Let's look here. We are given that the velocity, we will need the velocity, is that ABC centimeters per minute. I need it actually assigned here because we have some other calculations we'll do from it. We need the diameters, the 20 micrometers. We have theta. Theta 1 is 35 degrees given here. Theta 2 is equal to 20 degrees. What else is given here? We know that the length is 1 millimeter, was given in the problem statement. That's this section is 1 millimeter in length. We also are told that the pressure is 10 millimeters of mercury, and we need to define 10 millimeters of mercury. The millimeters of mercury is the same as 133.32 pascals. We need to label that as a unit. I may need the density, so that's defined there. Okay. All right. So now let's go to our calculate. So some of the key, and I'm going to move a copy of this down here so you can see it while we do the problem. So the first thing we have is the mass equation, simplified for open and steady state and non-reactive, is going to give us that m dot I minus m dot j is equal to 0 because it's steady state, open, and non-reactive. That's going to get simplified to basically that m dot I equals m dot j, so I'm just going to call them both m dot, and I can calculate m dot. It was given here, so I know the in and the out are both that same value. Now let's go to probably part of this given information. We can also put our unit vectors in because they are the information provided that we need for those. So the unit vectors, or the n dot I, is going to be equal to n dot I. The n dot I is this. Well, n dot I is the unit vector pointing out of the input. You'll notice that it's in the negative x direction, and the x component is going to be the negative cosine then of this 35 degrees because it's the angle is with that lower angle. So that's theta 1. And then you'll notice that the y vector of ni, the y component of ni, is also in the negative y direction. So that's going to be the negative of the sine of theta 1. And then there's no component in the z direction. Now we need n dot j is going to be equal to, that's the unit vector coming out of the top out port. You'll notice that the x component will be in the negative x direction, and it's basically so then it's the negative of the cosine of 20 degrees, or theta 2. But the y component of the nj, you'll notice, is in the positive y direction. So this is going to be the positive sine of theta 2. So here's our unit vectors. These are vectors of length 1 that are perpendicular, pointing out from the surface in the flow of the flow. So there's the ni, and there's, I need to put 0 in the z direction. And there's the unit vector in the out term. So now let's do our momentum equation. Our momentum equation basically is, we'll just do the linear momentum, is that the m dot n, which is m dot, times the v dot I, the velocity going in, minus m dot times v dot j, plus fp, which is the pressure forces, plus fb plus fr equals 0. So if we rearrange this equation here, we get Fr, the force we're looking for, is going to be equal to, and it's going to be the negative of, we're going to take everything else and put it on the other side of the equation here. So we basically, the unknowns we have right now that we need to calculate from this information is the velocity in, the velocity out, the pressure force, and the body force. So let's start with VI. That's going to be equal to, well, and I should probably actually call this the speed, because this is the speed that the fluid is flowing. It doesn't have direction, so it's not a velocity. So the speed here, the velocity is going to be the speed times, and you'll notice that the vector VI is going in the opposite direction compared to NI, the unit vector NI. So it's going to be times the negative of N dot I. Take the negative n dot I, it turns it around, is pointing the same direction as VI. So if you multiply the speed, the magnitude of the velocity, times the unit vector, the opposite of NI, which will be a unit vector then pointing in the same direction as VI, then you'll have the velocity of VI. And then Vj is going to be equal to that speed times, now in this case, if you look at Vj and Nj, they're both pointing in the same direction, so now we can just multiply by Nj. We don't need the negative to turn it around. So that's the velocity in the out port here. Now, so we've got Vi, we've got m dot calculated, we got Vi calculated, Vj calculated. Now we need the pressure force, so let's calculate the pressure force. So how do we calculate the pressure force? Well, the pressure force is going to be the sum of the pressure, the forces due to the PI and the PJ. With this, where pressure force generally is minus the pressure times the unit vector times the area of the flow. So and then the summation of those. So let's do, pressure force is going to be equal to, it's going to be minus PI, which is, they're both 10, so it's just P, times, now you'll notice that NI and PI are in opposite directions. That's why there's this minus here, is because pressure is always opposite the N. That's why there's pressure here. So this minus P is so that we can multiply by NI, and then times the area. And the area of the in and the out are the same, and it's the same as the area we calculated before. So we'll use area. And so there's the pressure force for the input, so FPI, let's say, and FPJ is going to be equal to minus P times N dot J times area. And so then FP is equal to the sum of those, FPI plus FPJ. Now, we need the body force. So the body force is going to be equal to the mass of the system times gravity. And in this case, it needs to be the vector of gravity, which is 0 newtons in the x direction, minus g in the y direction, and 0 in the, where g, you'll notice, is equal to 9.8 meters per second squared. That's a constant in MathCAD. All right, so here is our, oh, that's not the body force, that's the body force, the mass of the system times this vector for the gravity. So we need the mass of the system, and the mass of the system in this case is going to be equal to the volume of the system times its the fluid in the system times its density. So the volume is going to be equal to the length times the pi times d over 2 squared, right? Let me make sure that the diameter, yep, d was a small d. So that should be a volume, right? Yep, that's the liters. Let's make microliters by defining microliters as 10 to the minus 6 liters. So we've got microliters there. Now, with that, we can make this here, bring it down, and we should be able to turn it into that kind of equal now. And should we do micrograms here? Let's define a microgram. 10 to the minus 6 grams. There we go, in micrograms. Now, so now FB then, we can take this equation that we made, put it down here and turn it into a equal here. So there's our, those are also newtons. So here's the body force, we've got the pressure force, and we've got the velocities and the mass. So now we can just take this equation, turn that into an equal sign, and let's see how it goes. Oh, FB, the units are, okay, what's FB equals? Let's see what happens. Why is it doing that? Yeah, doesn't like me putting the newtons inside, I guess. All right, so there's our answer. We have in newtons, very small. Maybe we can try micronewtons. So there's the reaction force required to hold this tubule here in place under the conditions that were given in the problem statement. So now you just finish up with a finalize and provide a restatement of the solution. If you want to figure out what the magnitude of this is, right, you could do the square of the sum of the squares, square rooted. Will give you the magnitude of FR. This gives you the direction, the vector components.